All right, in this assignment, we're going to be learning how to read in data from the web and calculate underwater light fields using the Lambert Beer law. So I'm going to go ahead and make a comment here at the top of the source code. Assignment, we will learn how to read in data from the web and calculate underwater light fields using Lambert the Lambert Beer law. Okay, all right. So first of all, we're going to require a package, and hopefully you have this. If you don't, you can see. So I've got it. It loaded. If you get an error, you can go up here to Tools, go to Install Packages, and type Fields in here, and go ahead and click on that and hit Install, and it'll install it for you. So once you have that loaded and installed, we can read in sunlight data from the web. These are average daily radiances at the surface of the ocean somewhere in the North Atlantic. Okay, so we're going to read these from this site, modata.coe.udel.edu. It's going to be the 10-year irradiance file. So I'm just going to copy this link address. I'm sorry, let me show you where that is. So here it is. I'm going to be reading it from modata.coe.udel.edu. Public mass 627. You can navigate there if you want. This is the file we'll be reading in, so I'm just going to copy the link address and I'm going to paste it in here. Okay, and then I'm going to put in front of here sunlight equals read.csv, this thing, put this in quotes, and header equals true. Okay, so I'm going to go ahead and copy and paste this thing. Okay, so sunlight comes in, it's got 3,653 observations of two variables. We can look at the head of it, sunlight. So here's our sun time in text, and we'll deal with that in a minute. And here's then our modeled light. So this is 10 years of light. For this exercise, we're only going to use the first year of data. So we're just going to take the first 1 to 365 days. And remember, this is how we do that in that matrix notation. This is a matrix. We're going to take the first 365 rows, both columns, and this is going to overwrite our sunlight. So we're going to see this number drop here down to 365. So we have 365 observations now. All right. So the next thing we want to do is deal with the date. I'm actually going to just put a note in here first. This truncates the next thing we're going to do is deal with the date. So we have to tell there's lots of ways to deal with dates. So we have 7 days of the week, different months, different years, time zones, seasons, all those different things that R doesn't necessarily know about but can handle, but we have to tell it how to deal with it. So we're going to make an object called sun time. I'm going to create it, and this is going to be sun. We're going to use a function called as.date. Sunlight, the first column, and we're going to give it a time zone, is GMT time. So when we do that, it says unknown time zone. Warning message, but it still worked. And let's take a look at as.date. Yeah. Oh, maybe it wants UTC instead, which is the same as GMT. Okay, there we go. All right. There it is. And so now we can make a plot. Let's plot sun time, and actually before we do that, what we need to do next is convert our sunlight into PAR, photosynthetically active radiation. So PAR is now going to be sunlight, the second column, which is our values here. Remember in class we said approximately 41% of that is photosynthetically active radiation. So we're going to go ahead and run that. And just as a note, I'll put this in here. This is in units of watts per meter squared. Okay. So we can make a plot now of sun time and PAR. Okay, there it is. Go ahead and move this up. Sun time and PAR, and we could dress this up. Type equals overplot, which is lines and dots. You can see a little line in there. Okay, all right, sounds good. So what we have to do now is propagate these surface values, which are low in January, high in July, and low in January again. So high in the summer, low in the winter. So we know we're in the northern hemisphere. We need to propagate these surface values down. And the way we're going to do that first is by a couple things. We're going to create a depth vector. So z, our depth z, is going to be from minus 100 to 0. So that's 101 elements. And we need to set an attenuation coefficient. And that's units in meters to the minus 1. So let's turn it to K, and let's make it 0.05. All right. So now we need to create a field of underwater solutions from the Lambert beer law. So what we're going to do is we're going to loop over time. So we're going to make one water column per time value here. So that's going to leave us with a matrix or a field of values. And so those values need to be stored somewhere. We're going to call this UI.field_1, our first underwater light field. And we're going to make it null. Why are we making it null? Well, we're just creating it. Creating the field that will be, filled with underwater light values. Okay. So we're going to solve this in a more complex way than we need to, because later on when we use this code, we'll have varying underwater light values. Right now we just have a constant, so we're going to make it a little more complex than we need it to be, but it'll actually help us in future. So here we go. How are we going to do that? We have to loop over time and over depth in order to create this thing. So let's start by doing a for loop for x in 1 to the length of PAR. So it's looping over all the values of PAR, which are 365 of them. And then I'm going to put this little end notation in here. This is going to be the end of the x loop. We're going to do something. So remember, we're going to we're going to loop from x1 to the length par. If we want to do something interesting, we can just print par, the xth term, and if we run this, this should print out every term in par. There it is. All right, prints it out every single time. So when it loops through it the first time, it prints out the first value of par, then the second value of par, then the third value. That's what this does. But we're going to do something else with the par value. What are we going to do? We're going to make this something called ui.vec. We're going to turn that surface par value into an underwater vector. So right now, if I run this again, nope, unexpected. Oh, that was right. Okay, so let's do this. We ran this, so x right now equals 365. Just type x because it ran just a loop from 1 to 365. And so ui.vec should represent the 365th value of par. So we type par in here. You'll see the last one is 39. This is the 365th is 38.96136. Which is what UIVec is at the moment. So all this is doing is every time it's looping, it's creating a thing called UIVec, and it's dumping the xth element in there. So it's when x equals 1, it's the first element. When x equals 2, it's the second. When x equals 3, it's the third, so on. All right, what we're going to do now is propagate that with depth. So we're going to put another for loop in here for y in 2 to the length of z. All right, why are we doing 2 to the length of z? So what is z? Z is, oh, we haven't created z yet. There it is. I forgot to actually run that. Z and k. So z is a length of 101 from 0 to, from negative 100 to 0. You'll see why we're doing it backwards in a minute here when we go to plot it. But when we compute this, we want to take this one level down, right? So every meter down, we want it to go down. So we have for y in 2 to length z, we want to compute the Lambert beer. So the surface one, ui.vec, is always going to be our surface value. So we want to start at the second one. So that's going to be where depth is equal to minus 1 and 2. You'll see that come out here in just a minute. So we're going to do ui, we're going to create something, ui.vec y minus 1 times the exponent of k times minus 1. Okay, so this is the Lambert-Beer law with delta z equal to negative 1. Okay, so when ui.vec, let's try x equals 1, then we run this thing. Okay, so now ui.vec is the first element in par. We want to create ui, so we're going to do from 2 to length z, ui.vec 2 minus 1, so if we stick 2 in here at y, that is going to give us the first element of uivec, times the exponent. Okay, so this is going to solve for the next one down, the next one deeper. Oh, y equals 2. ui, so it's a little dimmer, right, because we put it through a diffuse attenuation coefficient, and now we're going to take that result and append it to uivec. So ui.vec is now a concatenation of what was in there, originally our surface value, and now our depth at 1 meter, ui. Okay, so now when I end of a y loop, if I run this y loop, and look at now UI.vec, you'll see that it's full of light values. Starting with, here's our surface one that we imported up here, and then every single one after that is the result of this while loop appending a value of light as it gets attenuated with depth. All right. Now we got to take that vector of light, which is just one depth profile at each time, and we go to the next one, but we have to store it somewhere. So this is how we're going to store it. We're going to do UI.field, which is already created, but it's empty. Remember, it's right here. Field underscore 1 equals rbind UI.field and underscore 1, and we're going to do the reverse of the UI.vec because our depths are upside down. We're going from -100 to 0. So we want the lowest one, lowest value. So right now if we look at UI.vec, it goes from the highest value to the lowest value. We're just going to use this reverse function to just reverse the order, going from the lowest value to the highest value, and that's going to map onto our z values, which go from the lowest to the highest. So that's going to work out. And there we go. So if we run this whole thing, come up here and start with z equals 100, and we look at the dimensions of UI.field 1, it's 365 rows by 101 columns. So every row represents a time period here along this graph, and we're going to propagate down that with depth. And so now we have a field of data, and we're going to show you how to, we're going to make a color map. Okay, and do a function called image.plot, which is a great function. Our x value is going to be sun time, our y value is going to be z, which is our depth, and then our field is going to be UI dot field underscore 1. Okay, and let's go ahead and give it a y label and x label equals time. Okay, there it is. Beautiful, right? So here in January, it's brighter at the surface, darker down below, but as we move into the season, you see it gets brighter, and then that light penetrates more and more, right? This is constant attenuation until we come back over here. So here's our values now, watts per meter squared. So low values are close to 0, red values are close to 140, and we can also do the same representation of this data just a little differently. Make a contour plot. Underwater light field, okay. I'm going to do contour, and then essentially it's the same arguments that go in here. There it is. Okay, so we have no more color bar over here, but we have an isolume at 20. What is an isolume? It's the depth of constant light. So everywhere here, this is the depth of the 20 watt per meter isolume. So it's shallower in the wintertime, deeper in the summertime, and then we get, you know, brighter lights up in here. And what's really cool with the contour function is that you can set a level. Let's say you want to look at the 10 watt per meter isolume and run that. Boom, there's the 10. Or the 1 watt per meter isolume. There's the 1. It's really deep. So in the wintertime, it's down around, looks like about 75 meters deep. Goes down to close to 100 and then back up again. Okay, so go ahead and check this out. And there's a homework assignment associated with this. And don't forget to save your code. All right. Thanks.